in the last lecture we saw the wave propagation in a medium which is not ideal but a good dielectric. Now we investigate the wave propagation in a medium which is a good conductor. That means in this medium the conduction current is much larger compared to the displacement current. So let us take a medium which we call as the good conductor. As we characterized earlier, a good conductor is characterized when sigma is much larger compared to omega epsilon or omega epsilon 0 epsilon r. So that means if the conduction current density is much larger compared to the displacement current density, then we call that medium as the good conductor. As we did in the previous case, again we find out what is the propagation constant for this medium. We separate the real and imaginary parts, and from there we get what is called attenuation and phase constants. So as we have seen, the propagation constant gamma for this medium will be square root of j omega mu into sigma plus j omega epsilon or epsilon 0 epsilon r. If I now substitute this condition that sigma is much greater than omega epsilon 0 epsilon r, this approximately can be written as j omega mu into sigma, because this quantity now is negligible compared to this quantity. So if I have a good conductor, essentially the displacement current contribution is neglected now, and because of that we have the propagation constant which is essentially given by that. Now if we separate the real and imaginary part of this, the square root of omega mu epsilon is straightforward. We want the square root of j, so the square root of j can be written as square root of j can be written as e to the power j pi by 2. So this is equal to square root of j pi by 2, so that is e to the power j pi by 4, that is equal to 1 upon root 2 plus j 1 upon root 2. So if I substitute this into that, I will get this quantity propagation constant gamma, that will be equal to square root of omega mu sigma to 1 upon root 2 plus j 1 upon root 2. So as you have done earlier, the real part of this quantity we call as the attenuation constant, and the imaginary part we call as the phase constant. We have for this medium the attenuation constant alpha is equal to square root of omega mu sigma upon 2, and we have phase constant beta, that is equal to square root of omega mu sigma upon 2. That is, for this medium the attenuation constant alpha and the phase constant beta are almost equal. So we have here alpha is almost equal to beta. Now if we go back to our understanding of transmission line, we had characterized the transmission line as a lossy line whenever we have the attenuation constant comparable to the phase constant. In this situation, the attenuation constant is equal to the phase constant. That means this medium, if we have at all, we want to visualize similar to the transmission line, this is a extremely lossy transmission line. So, for a good conductor, since the attenuation constant is equal to the phase constant, this medium is like a very lossy line case. That means when the wave tries to propagate in this medium, its amplitude dies down very rapidly in the direction of propagation. So, that means when that wave tries to enter the medium, the conducting medium, its amplitude reduces very rapidly because it is having a attenuation constant which is equal to the phase constant. So, a good conducting medium can be visualized like a extremely lossy transmission line. However, there is a small difference between a lossy transmission line and a conducting medium. In a lossy transmission line, the power was getting lost into the resistance of the line or the conductance of the medium separating the two conductors of the line. So, there was a loss of power when the wave propagated along the transmission line. However, in this case, when the wave is attenuating, not necessarily the power is getting lost into the conductor. In fact, we will see little later when we have a case when sigma equal to infinity. So, alpha becomes equal to infinity. That means over a zero distance the wave will die down as it tries to penetrate this medium. But in the small thickness there is no power loss. So, we will see that when we talk about the conductors, the wave cannot penetrate this medium because the alpha is very large, there is a lot of attenuation. That does not mean that the power is getting lost into the heating of the medium. Something else happens to the power, and that we will investigate little later. However, at this point we can say that a good conductor can be characterized like a lossy transmission line, and that is the reason we can have this quantity alpha equal to beta, and then the wave amplitude will vary as e to the power minus alpha into x, where x is the direction of the wave propagation. So, if I plot the amplitude as a function of x, the wave amplitude, if I plot this, I will get essentially a exponential curve which is this law. So, if I travel a distance x equal to 1 upon alpha, then the wave amplitude would die down to 1 over e of its initial value. So, if I take this value is 0 and I have a certain the wave amplitude at x equal to 0 here, over a distance of 1 over alpha, the wave amplitude would die to 1 over e of its initial value. So, I can say now that when wave tries to propagate in this medium, the conducting medium, effectively the propagation of the wave is over this distance, which is x equal to 1 upon alpha, because beyond this the field would become very small. So, what we can do is we can, as a rule of thumb, we can say that effectively the wave is going to propagate over this distance in this medium. This is the effective length over which the propagation of the wave takes place from the beginning of the medium. What that means is that any electromagnetic wave cannot really go deeper into the conducting medium. Basically, this tries to penetrate little bit from the surface of the conductor, or what that means is essentially the energy is in the dielectric medium. When this energy in the form of electromagnetic waves tries to go inside the conducting medium, it can penetrate only a short distance from the surface of the conducting medium, and deeper into the conducting medium the fields are negligibly small. So, essentially this creates some kind of a surface phenomena on the conducting surface. So, if I say this is the effective width over which the wave propagate, I can now say that beyond this the medium does not exist, because there are no fields beyond this point. So, no matter what is the thickness or the depth of this conductor, only this thickness where the field died down to 1 over E of its initial value, they are the one which simply matter in the propagation of electromagnetic wave. Beyond that, whether the what conducting medium is there, it does not really affect it. So, in practice, whenever we are having the boundaries which are conducting boundaries, essentially this region which is very close to the surface of the conducting boundary, that's what will decide the propagation characteristics of the electromagnetic wave. What is deeper in the medium, it is of no relevance, because the fields essentially die down very rapidly as we go inside the conducting medium. So, if I write for this alpha over this depth, whatever this quantity is, let us call that quantity as delta. So, I have here depth, effective depth, let me call that quantity as delta, which is 1 over alpha. So, if I substitute for the value of alpha from here, that will be square root of 2 upon omega mu into sigma. If I substitute for omega, which is 2 pi into frequency, that will be equal to square root of 2 upon 2 pi f into mu into sigma. 2 will cancel. So, from here essentially I can get square root of 1 upon pi f mu sigma. So, I have an effective depth of penetration of the electromagnetic wave inside a good conductor that is inversely related to the square root of the frequency. It is inversely related to the square root of the conductivity. So, higher the conductivity or higher the frequency, less will be the depth of penetration. Not only that, when the conductivity is infinite, that means if I take the ideal conductor, in that case this depth will be 0, that means the wave will not penetrate the medium at all. So, if you take an ideal conducting medium, there is no penetration of electromagnetic energy in the ideal conductor. Similarly, if I go to very arbitrarily high frequencies, the depth of penetration becomes extremely small. Let me take some typical numbers, and just to get a feel for what depth we will have if we operate at the radio frequencies. So, let us say I take some arbitrary medium for which the conductivity is approximately 10 to the power 7 mhos per meter, which is a good conductor, and let us say I take a frequency f that is 100 megahertz, a typical frequency which is used for the TV transmission or for the radio propagation. Now, from here if I substitute for this effective depth delta, I get this delta is equal to square root of 1 upon pi into frequency which is 100 megahertz, so 10 to the power 8 hertz. So, this is into 10 to the power 8 into mu, and let us assume that the permeability of this medium is same as the free space, which is 4 pi 10 to the power minus 7. So, let me assume here the permeability of this medium mu is equal to mu 0, which is equal to 4 pi into 10 to the power minus 7 Henry per meter. So, I can write here 4 pi into 10 to the power minus 7 multiplied by sigma, which is 10 to the power 7. if I simplify this, this will be 1 upon 2 pi into 10 to the power 4, or this is in meters, this is meters. I can multiply this by 10 to the power 6 to make it micrometers. So, this will be approximately about 15 micrometers. So, if I take a medium good conductor which is having a conductivity of the order of 10 to the power 7, and let me remind you that a good conductor like copper has a conductivity of 5.6 10 to the power 7, the silver has a conductivity even higher than this. So, if I take a good conductor material in practice like copper or silver, and if I take the frequency, let us say 100 megahertz, the depth of penetration of the electromagnetic wave is only 15 microns. That means the wave propagation is just 15 micron from the surface of this good material which is having conductivity 10 to the power 7. And as we saw, as the frequency increases, the skin depth becomes even smaller. So, if you go to frequency of gigahertz, like frequency which are used for satellite communication, or the microwave frequencies or millimeter wave frequencies, this number will become even smaller. So, what we find is that effectively for a good conductor, if you take the frequencies which are typical radio frequencies, the depth of penetration typically is of the order of few microns, a few tens of microns. So, basically this phenomena is taking place only on the skin of the material, which is of this order, few micron to few tens of micron. That is the reason we call this effective depth as the skin depth of the material. So, we call this quantity delta, okay, effective width, as the skin depth of the material. So, skin depth is a parameter which tells you over which the electromagnetic energy is going to exist from the surface of a good conductor. So, beyond this depth, again as I mentioned, the properties of the material do not really matter. So, if we have a high frequency system, a component, since the energy is going to lie or the fields are going to lie only within a distance of few tens of microns, we have to make that layer very good, because any perturbation in the properties of that layer are going to affect the propagation of electromagnetic wave. So, if I have, let us say, a solid conductor and I want to send some high frequency signal using this conductor, the fields are essentially going to lie only on the surface of that conductor within the skin depth. So, if I take a conductor, let us say something like that, and let us say the electromagnetic energy is going to propagate along this conductor, the current which are going to be excited because of these fields are not going to lie in the entire cross section of the conductor, they will essentially be confined to the skin depth of the conductor. Only this is the region where the fields are going to exist, and because of that the currents are going to flow. So, this region, though you are having conductor here, is not really contributing to the flow of the current, because the current is just confined to this, where this thickness is delta, which is typically of the order of few tens of microns. So, even if you make this conductor hollow, the propagation of the energy along this conductor will not get affected, because the layer, which is this layer, it still remains intact. So, two things happen here. Firstly, that since the phenomena is only taking place on the surface, this material does not play a role in the propagation of electromagnetic energy. Secondly, if you wanted to have a good propagation, the properties of this small thin layer should be very good, because any perturbation in the conductivity of this layer would affect the properties of the electromagnetic waves significantly. So that is the reason when we go to the microwave components where the frequency is very high and the skin depth becomes only a micron or something like that, the surface has to be extremely good and perfect, because any small perturbation on that surface where the most of the energy is confined to will affect the propagation of electromagnetic wave. Once we understand this, then we find something interesting now, and that is, let us say we have a finite conductivity of this medium through which we were sending the signal along this conductor, and we have certain area of cross section or the radius for this. If I go to extremely low frequencies, the current will be uniformly distributed over this, so I can find out what is the area of cross section. From the area of cross section I can find out what is the resistance of this wire per unit length, because I know the resistivity of the medium. However, as we increase the frequency and as the skin depth starts coming into picture, the current is now getting more and more confined to the surface. That means the area of cross section over which the current is flowing, that is reducing now. As a result, the resistance of this conductor starts increasing as you go to high frequency. So because of the skin depth, the resistance now becomes a function of frequency. For a given conductivity, as the frequency increases, the skin depth reduces. As the skin depth reduces, the area of cross section over which the currents are flowing, that reduces, and because of that the resistance of the conductor increases. So what we find now, that the resistance which we treated more like the property of the wire is not so when we go to high frequencies and when the skin depth starts playing a role. So as we go to higher and higher frequency, the same conductor starts showing more and more resistance, and the wave propagation essentially is confined to the surface of the conductor. Another aspect of the high conductivity of the medium is, if you look at the characteristic impedance of this medium or the intrinsic impedance of the medium, eta c, this is, as we saw earlier, this is j omega mu divided by sigma plus j omega epsilon, and now we are having sigma much larger compared to omega epsilon. So this is approximately square root of j omega mu divided by sigma. Again, if we separate the real imaginary parts, the intrinsic impedance of the medium will be square root of omega mu upon 2 sigma plus j square root omega mu upon 2 sigma. Or if we write in terms of the magnitude and phase, this quantity will be square root of omega mu upon sigma angle 45 degrees. If you recall, the electric and magnetic fields in a medium are related to this quantity, what is called the intrinsic impedance of the medium. We have seen for dielectric medium or for medium that the magnitude of the electric field and the magnitude of the magnetic field, they are equal to eta. So in this case, again the ratio of this will be equal to the characteristic impedance or the intrinsic impedance of the medium, and this quantity now is the quantity which is omega mu upon sigma angle 45 degrees. So what we now find is there is the electric and magnetic fields are perpendicular to each other, the transverse electromagnetic wave nature is still there, but now there is a time lag between the magnetic field and the electric field. So, if you can take the ratio of these two, the ratio is now dependent on frequency also, not only on the medium parameter that it used to be in the case of dielectric medium, and also the magnetic field now lags the electric field by 45 degrees. So, when we talk about a good conducting medium, important things happen, that when the wave tries to penetrate the interconducting medium, it penetrates over a very short distance, what is called the skin depth, and also the electric and magnetic fields are not in time phase anymore, but there is a phase difference in time for the electric and the magnetic field, and which is for a good conductor is approximately 45 degrees. So, what we find from this discussion is that the wave propagation in a dielectric medium and in a conducting medium are completely different. In a dielectric medium, the wave can really go deeper into the medium, the electric and magnetic fields are in time phase, the wave amplitude reduction is very small, whereas if I go to the conducting medium, the wave attenuates very rapidly, it cannot really go deeper into the medium, also the electric and magnetic fields have a phase difference in time with each other. If we take a general medium now, which is a combination of the dielectric and conductor, then of course all these relationships are going to be complex, we cannot make any approximations. So, for those media for which the conduction current is comparable to the displacement current, of course we have to do the detailed analysis, but in the two extreme cases, for good dielectric and for a good conductor, these approximations can be made easily and one can understand the wave propagation in a more comprehensible manner than in a general medium. With this understanding, now we go to the another aspect of the wave propagation, and that is what is the velocity of the wave when it tries to move into this medium. Now, first let us take a medium which is again a good dielectric, and without losing generality, let us say the losses in the dielectric are very small. So, I can treat this dielectric as almost like a lossless dielectric, and then let us ask a question, how the wave is going to propagate in this medium. So, as we have seen, if the medium was lossless, then the propagation constant is purely imaginary, and then any field E can be written as some E0 e to the power minus j beta x, and if I want to put explicitly the time function, it will be j omega t. I can combine this to get the amplitude vector E 0 e to the power j omega t minus beta x. And as we have seen earlier, this phenomena essentially represents a wave phenomena, the wave is travelling, and in this case when we take minus j beta x, the wave is travelling in positive x direction, that we have already seen. Now, if I stand on a particular location in the space, that means if x is constant, and look at the wave which is moving in the space, the phase of this wave will be varying with respect to time as omega t. That means the phase is linearly increasing as a function of time. If I instantaneously look at the wave in the space, again we see that the phase is varying as minus beta x, that means again it is varying linearly as a function of distance in the space. So, if we become an observer and stand in the space and look at the wave which is moving, then at any particular point of the wave, if we monitor, its phase will vary linearly as a function of time. However, suppose I hold on to a particular phase point on the wave. Let us say this is the wave. If I take any particular point and I hold on to this point, so as an observer we are not standing and watching the wave moving, but let us say we are holding on to a particular phase point on the wave. So this is the point, let us say I want to hold on to. Now since the wave is moving, if I have to hold on to a particular phase point, I must move along the wave, then only I will hold on to this point, otherwise the wave will simply move and the phase will change. So an observer has to move along with this wave with a velocity with which the wave is traveling, if he does not want to lose this particular point to which he is holding on to. Or in other words, now if the observer is not losing this point, if you look at the wave, if you look at the face of the wave, for him the face is not changing anymore, because he is holding on to this point, he is looking at the wave, and for him the face is always same, because he is moving with the wave. So if we consider an observer such that he holds on to a particular point and does whatever is needed not to lose this point, then for that observer the phase appears to be constant as a function of time. So what we do, we take this quantity, the phase, total phase of the electromagnetic wave, and if I make this quantity constant as a function of time, if I make this stationary as a function of time, whatever speed the observer has to move to make this stationary, that we will say is the velocity of this wave. So what we say is that make the phase stationary as a function of time to get the velocity of the wave. So if I say that this quantity, which is a total phase, which is a combination of space and time, if I make that constant, I say omega t minus beta x is constant for that observer which is moving with the wave with the velocity of the wave. Then from here, if I take a derivative of this with respect to time, I will get omega minus beta dx by dt, that is equal to 0, which will give me this quantity dx by dt, which is nothing but velocity, that is equal to omega by beta. Now since this velocity we have calculated from the stationarity of the phase, we call this velocity as the phase velocity of the wave. That means the constant phase point of the wave is moving with this velocity. Later on we will see this concept is essential, because there is another velocity with which actually the energy travels. In this case, when we are talking about an unbound medium, we have chosen a coordinate system such that the wave is traveling along x direction. This appears very trivial. However, in general, when we talk about the wave moving in some arbitrary direction, this concept of saying that the phase is moving with this velocity, but the energy might move with some other velocity, will become more apparent. So in this situation, when we have said that the phase is moving with this velocity, we call this velocity of the wave as the phase velocity. So we have explicitly say that this velocity is the phase velocity. Normally it is denoted by Vp, and that quantity is nothing but omega divided by beta. So the quantity Vp is not the quantity which people know a priori. For any medium, first for a given frequency we find out what is the phase constant, then omega by beta gives me a quantity which is velocity. That velocity we call as the phase velocity. So essentially knowledge of propagation constant or the phase constant is important, because that tells me what is the velocity of the phase of the electromagnetic wave when it travels into the medium. In fact, for a traveling wave this is very straightforward. So I get a relation which is like this. However, the concept of phase velocity can be extended to any arbitrary wave propagation. For example, suppose I have two waves which are traveling in opposite direction, which form the standing waves. I can still define the total phase, which is a combination of space and time, and by making that quantity stationary as a function of time, I may get the expression for the phase velocity of the wave. So the concept is very general, though for traveling wave it will be very simple, and then we get the phase velocity of a traveling wave which is equal to omega by beta. So we will see that this relation we will use very often when we go to the propagation of electromagnetic wave. Now, as we have seen earlier, if we take a dielectric medium, so if I take a pure dielectric, with dielectric constant epsilon r, if I take that medium, then for this medium the phase constant beta is omega square root mu epsilon 0 epsilon r. Since the medium is dielectric medium, even the permeability of the medium, permeability of the free space, so the phase constant is omega square root mu 0 epsilon 0 epsilon r. Now, first let us consider now a medium which is free space, that means for which the epsilon r is 1. So this is for this dielectric. For free space, your epsilon is equal to epsilon 0 and beta is equal to omega square root mu 0 epsilon 0. So the velocity for the free space, if I say v p in the free space, that is equal to omega divided by omega square root mu 0 epsilon 0, that is equal to 1 upon square root mu 0 epsilon 0. If I substitute for mu 0 and epsilon 0 in this will be 1 upon square root 4 pi into 10 to the power minus 7 into 1 upon 36 pi into 10 to the power minus 9. That will be equal to 3 into 10 to the power 8 meters per second. So this is the velocity of the wave when the wave is traveling in the free space, and that is 3 into 10 to the power 8 meters per second. It will immediately strike to us, this is the velocity of the light in free space. So since light is a transverse electromagnetic wave, it is traveling with the velocity which is given by this quantity, which is the phase velocity, and that is the reason the velocity of light is 3 into 10 to the power 8 meters per second. So any wave, not only light, but any wave which is transverse electromagnetic and is traveling in the free space will have a velocity which is equal to 3 into 10 to the power 8 meters per second. So what we can do is we can substitute from this one into this. So 1 upon square root mu 0 epsilon 0 is the velocity of light in vacuum, and normally this is denoted by a parameter small c. So essentially the velocity of wave in a dielectric medium Vp will be omega square root omega square root mu 0 epsilon 0 epsilon r, which is 1 upon square root mu 0 epsilon 0 square root epsilon r, and this quantity 1 upon mu 0 epsilon 0 is nothing but velocity of light in vacuum, which is c. So, that is equal to c divided by square root epsilon r. So, first thing to note here is that when the electromagnetic wave travels in a medium, it always slows down, because if this quantity is greater than 1, then the phase velocity will be always less than the velocity of electromagnetic wave in the free space, which is the velocity of light. So, velocity of any electromagnetic wave in a dielectric is always less than the velocity in the free space. We also know that the refractive index of the medium is defined as the ratio of the velocity of light in vacuum divided by the velocity of light in that medium. So, if I go by that definition, we know that we have the refractive index of the medium. Let us say we denote that by small n, that is equal to velocity of light in vacuum divided by velocity of light in medium. So, this quantity is nothing but c divided by Vp. So, that is c divided by Vp, which is nothing but square root of epsilon r. So, we have a very important relation, that is the refractive index of the medium, a lossless medium, is equal to the square root of the dielectric constant of the medium. So, whenever we have a medium which is pure dielectric or a good dielectric, the refractive index and the dielectric constant are related through this relation, and the electromagnetic wave always slows down compared to the vacuum when it enters any medium which is having a dielectric constant greater than 1. Same thing we can do for now the conducting medium also. We can take a conductor and no matter what small penetration the wave has inside the conductor, we can still ask what is the velocity of this. So, we again for this conductor we have beta, which is square root of omega mu 0 sigma upon 2. So, we can have the phase velocity Vp, that is omega upon beta, that is equal to omega square root omega mu 0 sigma upon 2. So, that is equal to square root of 2 omega divided by mu 0 sigma. So, the velocity which we had for a dielectric medium, which was c upon square root epsilon r, the velocity was not a function of frequency. So, if the dielectric constant of the medium is not a function of frequency, the velocity also is not a function of frequency. That means all frequencies travel with the same speed in that medium. However, if I take a medium which is a conductor, even if the medium properties are not varying as a function of frequency, the phase constant is a function of frequency and the velocity also is a function of frequency. This medium then we call as a dispersive medium because the velocity is varying as a function of frequency. So, when Vp is a function of frequency, we call this medium as a dispersive medium. So, what we find is that a medium which is conductor, the velocity becomes a function of frequency. That means all frequencies do not travel with the same speed, and because of that we have a dispersion in the medium. So, we have something important conclusions to draw now, that is, first of all, the electromagnetic wave when travels in the medium, we can define a parameter what is called the phase velocity. That is a parameter which tells you with what speed the phase or a constant phase point on the wave is traveling in the medium. Then we find that for dielectric medium, the phase velocity depends upon the dielectric constant of the medium, and for dielectric constant greater than 1, the phase velocity is always less than the phase velocity in vacuum. That means the wave always slows down when it travels in a medium with higher dielectric constant. However, a dielectric medium is non-dispersive medium because the wave slows down, but all frequencies travel with the same speed. Then we also find that the parameter what is called the refractive index of a medium, which is the ratio of the velocity of a wave in vacuum to the ratio of the velocity of the wave in the medium, is equal to the square root of the dielectric constant of the medium. And then when we go to the conductor, we find that the velocity becomes a function of frequency. That means the medium becomes a dispersive medium. So, a pure dielectric medium is a non-dispersive medium, but a good conductor is a dispersive medium. This essentially summarizes the propagation of the transverse electromagnetic wave in an unbound medium. Before we proceed further, now we investigate first the power flow associated with the electromagnetic waves, and then we will go to the more complex analysis of this, which is propagation of electromagnetic wave in bound medium or in a medium which are having at least the interfaces, dielectric or the conducting interfaces.